Tests of significance, the basics. In Chapter 17, we cover the reasoning of tests of significance, stating hypotheses, p-value and statistical significance, tests for a population mean, significance from table star, significance from a table, significance from a simulation. Confidence intervals are one of the two most common types of statistical inference. Use a confidence interval when your goal is to estimate a population parameter. The second common type of inference, called tests of significance, has a different goal: to assess the evidence provided by data about some claim concerning a population. A test of significance is a formal procedure for comparing observed data with a claim, also called a hypothesis, whose truth we want to assess. Significance tests use an elaborate vocabulary, but the basic idea is simple. An outcome that would rarely happen if a claim were true is good evidence that a claim is not true. The reasoning of tests of significance. Artificial sweeteners in colas gradually lose their sweetness over time. Manufacturers test for loss of sweetness on a scale of -10 to 10, with negative scores corresponding to a gain in sweetness, positives to a loss of sweetness. Suppose we know that for any cola, the sweetness loss scores vary from taster to taster. According to a normal distribution with standard deviation sigma equals 1, the mean mu for all tasters measures loss of sweetness and is different for different colas. So the mean mu for all tasters measures loss of sweetness and is different for all colas. Here are the sweetness losses for a cola currently on the market as measured by 10 trained testers. 2.0, 0.4, 0.7, 2.0, -0.4, 2.2, -1.3, 1.2, 1.1, and 2.3. The average sweetness loss is given by the sample mean X bar equals 1.02. Most scores were positive, that is, most tasters found a loss of sweetness, but the losses are small, and two tasters, the negative scores, thought the cola gained sweetness. Are these data good evidence that cola lost sweetness in the storage? We make a claim and ask if the data give evidence against it. We seek evidence that there is a sweetness loss, so the claim we test is that there is not a loss. In that case, the mean loss for the population of all trained testers would be mu equals 0, so no loss. If the claim that mu equals 0 is true, the sampling distribution from X bar, the sampling distribution of X bar from 10 tasters is normal with a mu equal to 0 and standard deviation equal to sigma divided by root n, which equals 2 divided by root 10, which is 0.316. This is like calculations we did in chapter 15. We can locate our X bar of 1.02 in this distribution and comment on whether it is surprising. Stating hypotheses. A significance test starts with a careful statement of the claims we want to compare. The claim tested by the statistical test is called the null hypothesis, or H naught, H subscript 0. The test is designed to assess the strength of the evidence against the null hypothesis. Often the null hypothesis is the statement of no difference. The claim about the population that we are trying to find evidence for is the alternative hypothesis, or HA, the H with the subscript A. The alternate is one-sided if it states that the parameter is larger or smaller than the null hypothesis value. It is two-sided, the alternate is two-sided if it states that the parameter is different from the null value, meaning it could either be smaller or larger. In the sweetness example, our hypotheses are that the null hypothesis is mu is 0. There's no change. There's no change in sweetness at all. The alternate hypothesis is that mu is greater than 0. So there is a change. The change is a decrease in sweetness, which is ranked as a positive number. So positive greater than 0. The alternate hypothesis is one-sided because we are interested only in whether the cola lost sweetness. Example, does the job satisfaction of assembly workers different when their work is machine-paced rather than self-paced? Assign workers either to an assembly line moving at a fast pace or to a self-paced setting. All subjects work in both settings in random order. This is a matched pairs design because you'll work in both groups at some point. After 2 weeks in each work setting, the workers take a test of job satisfaction. The response variable is the difference in satisfaction scores, self-paced minus machine-paced. The parameter of interest is the mean mu of the differences in scores in population of all assembly workers. The null hypothesis states that there is no difference between self-paced and machine-paced work. That is, H naught is that mu equals 0. The author of the study wanted to know if the two work conditions have different levels of job satisfaction. They did not specify the direction of the difference. The alternate hypothesis is therefore two-sided, just not equal to. So the null hypothesis is that mu is not equal to 0. There is some difference. The null hypothesis H naught states the claim that we are seeking evidence against. The null hypothesis states the claim that we are seeking evidence against. The probability that measures the strength of the evidence against the null hypothesis is called the p-value. Let me read that again to you. The probability that measures the strength of the evidence against the null hypothesis is called the p-value. A test of significance, a test statistic calculated from a sample data measures how far the data diverges from what we expect if the null hypothesis H naught were true. Large values of the statistic show that the data are not consistent with H naught. The probability computed assuming H naught is true that the statistic would take a value as extreme or more extreme than the one actually observed is called the p-value of the test. The smaller the p-value, the stronger the evidence against H0 provided by the data. So if the value is large, it's going to be off into the tiny little tails of our bell-shaped curve, right? Our normal distribution. Small p-values are evidence against H0 because they say that the observed result is unlikely to occur when H0 is true. Large p-values fail to give convincing evidence against H0 because they say that the observed result could have occurred by chance if H0 were true. Tests of significance assess the evidence against H0. If the evidence is strong, we can confidently reject H0 in favor of the alternate. Our conclusion in a statistical test comes down to, if the p-value is small, reject the null hypothesis, conclude the alternate in the context of the problem. If p-value is large, fail to reject the null hypothesis, and you cannot conclude the alternate hypothesis in the context of your problem. There is no rule for how small p-value has to be. There's no rule for how small a p-value we should require in order to reject H0. It's a matter of judgment and depends on the specific circumstances. But we can compare p-value, we can compare the p-value with a fixed value that we regard as decisive, called the significance level. We write that as alpha, the Greek letter alpha. It's it looks a little like an A, but it has a tail on the top and a tail on the bottom of the right-hand side of the circle. So when you make an A, you do a loop with a little tail. When you make an alpha, that tail has an up-facing tail and a down-facing tail. If that's at all less confusing. When our p-value is less significant than our chosen alpha, we say that that result is statistically significant. If p is less than alpha, then our p-value is statistically significant. If the p-value is smaller than alpha, we say that the data are statistically significant at the level alpha. The quantity alpha is called the significance level, or the level of significance. And we're often given that value alpha. We want to follow the state plan, solve, and conclude. So the 4-step process for the test of significance is that we want to state, we want to plan, we want to solve, we want to conclude. So first you ask yourself, what's the practical question that requires a statistical test? That's stating the problem to yourself. And then make a plan. Identify the parameter, state the null and alternate hypothesis, and choose the type of test that fits your situation. For us as undergraduates, we are told which level of significance to use. When we solve the problem, then we carry out the test in 3 phases. Phase 1, check the conditions for your test that you plan to use. Phase 2, calculate the test statistic. Phase 3, find the p-value. And then in conclusion, you return to the practical question to describe your results in that setting. So do you accept the null hypothesis? Do you reject the null hypothesis? What does that mean in terms of the context of your problem? The z-test for a population mean. Draw an SRS of size n from a normal population that has known mean mu and known standard deviation sigma. To test the null hypothesis that mu has a specified value, then the null hypothesis H naught is that mu is the original mu from the problem, or mu naught. Compute the one sample z-test statistic. So just like in chapter 15, we are looking at what from chapter 3 started as x minus mu over sigma, now is transformed into our x being our test statistic, our mu being the given mu naught, and our standard deviation actually now being the standard deviation divided by root n, right? So we're using our chapter 3, which led us to chapter 15, right? Where we then had to start dividing our sigma itself by root n, right? And now x is our observable x bar and mu is mu naught. So just borrow what you know from the past to help build up your understanding of what we're working on now. So to compute the one sample z-test statistic, z equals x bar minus mu naught divided by the quantity of sigma divided by root n. In terms of the variable z having a standard normal distribution, the approximate p-value for a test of H naught against your alternate hypothesis. So got a couple pictures there. They don't all stay up. So when you're looking when you're trying to test the alternate being mu greater than the given value, because remember, mu naught is actually a number. So we're told a number here. So mu is greater than mu naught is saying z is greater than our z critical. So z critical here is also what we're looking at. And greater than, right, means that you're looking at a shaded area that is to the right of your z-score, or p-values that fall in that more extreme value. So looking at the next one, let me clear that screen for you. And now mu being less than mu naught is looking for the probability that your z score from above is more extreme to the left of a given critical z value. And our two-tailed test is just saying we don't know if the values of mu is more than or less than the mu that we're given, but we think it's not that mu. So it's either above it or below it, and we don't really know. So in this version, then you're looking at a normal curve where you have critical regions on both sides, and you're looking at then the absolute value of your z-score, because you'll have a plus and a minus on the left side and a plus value on the right side. So if your z is greater than, if your z from above is greater than or equal to the absolute value of your z critical, then we are in those critical regions. All right, let's look at an example. Executives' blood pressures. State the problem. NCHS reported that the systolic blood pressure for males 35 to 44 years of age has a mean of 128 and standard deviation 15. The medical director of the company finds that for 72 executives in this age group, that X bar, the mean, is 126.7. That's the average systolic blood pressure for these 72 males. It is the evidence that the company's executives have different mean systolic blood pressure from the general population. So is there evidence? Plan. Take mu to be the mean amongst all executives. So mu naught is the original mean for the population that we're told. NCHS reports that the systolic blood pressure for males, that's all males, 35 to 44. So all males are reported to have a blood pressure mean of 128. So our null hypothesis, which you remember looks like mu equal to mu naught is an actual number. So here, mu equals to mu naught reads mu equals to 128 because mu naught is 128. Our null hypothesis comes from the question, is there evidence that the company's executives have a different mean? So different just means either less than or equal to, but not that, right? Not 128. So here, mu is not equal to mu naught. That's what we're saying. So mu naught, again, is a number. That's the number 128. And mu naught is not equal to 128. That's what we're getting from the word different in the question. The alternate is two-sided because the medical director did not have a particular direction in mind before examining the data. So he wasn't saying less or greater than. So step 2 is in our process is to solve. So we stated the, I think we're at step 3. Let me take a look back there. We stated the problem, we made a plan. Now we're at step 3, solve it. Okay. As part of the simple conditions, suppose we're willing to assume that the executive's systolic blood pressure follow a normal distribution with standard deviation sigma equals 15. Software can now calculate Z and P for you. Going ahead by hand, the test statistic is Z equals X bar, our observed mean for the sample, minus mu naught, the mean given to us about the population, divided by the population standard deviation, which itself is divided by the square root of the sample size. 1.26.07 minus 128 in our numerator, divided by the quantity, 15 divided by root 72 in the denominator, equals negative 109, which if 128 is our mean, negative 1.09 tells us we're below the mean in our sample by about 1 standard deviation. Using table A or software, we find that the p-value is 0.2758. So in table A, you would find the row that said negative 0.10. You would follow that row over to a column that read 0.09. You would put those two together to come up with your negative 1.09. And in that intersection, you would find then the 0.2758. And then we make a conclusion. More than 27% of the time, because 0.2758 is 27.58%, so more than 27% of the time, an SRS of size 72 from the general male population would have a mean systolic blood pressure at least as far from 128 as that of the executive sample. The observed X bar, the observed mean of 126.07, is therefore not good evidence that executives differ from other men. Statistics in practice uses technology to get p-values quickly and accurately. In the absence of suitable technology, you can get approximate p-values by comparing your test statistic with critical values from a table. Significance from a table of critical values. To find the approximate p-value for any z statistic, compare z, ignoring its sign, that's the absolute value, with the critical value z star at the bottom of table C, which we used in chapter 15. If z falls between two values of z star, the p-value falls between the two corresponding values of p in the one-sided p or the two-sided p row of p side. Oh, sorry. Let me reread that. If z falls between two values of z star, the critical value, the p-value falls between the two corresponding values of p in the one-sided p or two-sided p row of table C. We saw in section 15.3 that we can approximate the sampling distribution of X bar by taking a very large number of SRSs of size n and constructing the histogram of the values of the sample means X bar. A corresponding method of taking a large number of repeated SRSs from the population distribution when the null hypothesis is true and using these approximate p-values is sometimes referred to as resampling. All we need to know is the population distribution under the assumption that the null hypothesis is true. We then resample many times from the population distribution, compute the value of the sample statistic for each sample, and determine the proportion of times we have obtained sample values as or more extreme than that of our actual data. This proportion is an estimate of the p-value. Comments about resampling. First, we must resample in the same manner that we obtain our data. If data are obtained by an SRS, we resample by taking repeated SRSs from the population distribution determined by the null hypothesis. Second, resampling only provided an estimate of the p-value. Repeat the resampling and you will obtain a different estimate. Accuracy of the estimate is improved by taking a larger number of samples to estimate the sampling distribution. Finally, resampling requires the use of software.